Please welcome Davit Kocharyan. He's from PicsArt, and he's going to introduce information retrieval search engine powered by ML. I see you already shared your presentation. Yeah, so please start, Davit.
Okay, thank you. Just one word before I start. Probably you already heard, so I kind of made a little bigger presentation that it was supposed to be, since I thought that it's going to be 1 hour length, but it's going to be 25-minute length. So I ask for apologies if we will go faster than needed through some derivations. So let's move on. Okay. So information retrieval, right? What is this? It's like a broad field that is discussing the approaches to find some material, data structured or unstructured, based on some given input or query. One of the biggest applications of this is a search engine that you all are very much aware of, Google, Yahoo, Bing, Yandex, and so forth. And also some industrial search engines that almost every company has, and PicsArt is not exception. We have our only search engine that searches for stickers, images, users, and stuff like that. So just a couple of words before we go to some machine learning applications about like what is actually the approach to search some stuff given the query. The most primitive approach would be if somebody searched for Anthony or Brutus, to go through all available documents and see if Anthony or Brutus are there as a terms or words. That would not be very efficient. Instead of that, we can come up with the term document matrix, where the rows are terms and the documents are columns. And these values could be binary or discrete, can show like whether this term present in this document or may just binary, or may show how many times. The approach to search, the most basic classic one that is still the foundation of most search engines, is a Boolean retrieval, where we pose our query as a Boolean expression that has terms that are connected by logical operators and or not, and look for results in that way. So for example, if somebody searched for Anthony Brutus, we will look for, in our document matrix for Anthony, we will look for Brutus, and then we will intersect the document lists and give the intersection if our logical operator is AND. So last important concept here is called inverted index. Obviously, this matrix, document term matrix, is going to be very sparse, since the term is not present. It's going to be present in a very few number of the documents. So in that case, we need just to store only the list of documents where it is actually located, and this list is called postings. And as I said, we can do any type of Boolean operations with them. We can union them, intersect them, and stuff like that. So this is just to give a sense of like what happens in the most high level way. So the query comes, we search in the index, and then in some way return results. So industrial search engine is a very big complex system that has a lot of building blocks, and some of them are here. So for example, documents indexing, that, for example, if it's web search, you need to crawl internet, collect, clean, and store URLs and web pages. If it's not, for example, in PicsArt is an industrial search engine, you still need to in some way process and store your, in our case, images, mainly. There is a part with query processing. So for example, when query comes, we need to somehow process it. We can't search exactly what the user had wrote. There is a stemming, lemmatization, autocomplete, spell check, also translation, transliteration, and a lot of stuff going here. But again, we will ignore those parts for those parts are kind of out of the scope of this presentation, since it's even not 1 hour, it's even 30 minutes. And it actually requires some machine learning applications as well, but mainly uses some already very well established engineering techniques, which is also an interesting topic in itself, but not very much related to the focus of our presentation. And another important part is that whenever we have some query that was processed, we need to somehow match it with the documents. Here we will talk about some, firstly about primitive approaches, and then about more advanced approaches. And then you need also to rank the documents in the order of decreasing relevancy to make sure that on top you get the most relevant documents. So the search is actually like a pyramid of different stages. So there's a clear hierarchy whenever you return results. So you start with the foundation with all available documents that you have in your database. Then you have some kind of alternative to, or like some version of inverted index that stores mainly, even now, the foundation of the search is still inverted index. It just could be more fancy and advanced than the one that I just showed you in the beginning. And then after you kind of get all documents that might be relevant to the query that the user has searched for, you do first level ranking, second level ranking. It could be 3, 4 levels. The main idea is that you start with something that is cheap computationally and fast, since you need to process millions or billions available documents. And then you move to some more advanced and more computationally heavy algorithms, because in the beginning, you need high recall. You need all available relevant documents. And then at the end, you need high precision, where out of all documents that might be relevant, you want to put on top the most relevant ones. And the idea is that since you have a low latency requirements, because it's search is also search engine is a very engineering, has a high engineering requirements. You have to provide results real fast. You can't afford to process it for half a minute. That is why if you use some computational heavy algorithms, they have to be at the end when the number of available documents is very small. That is why you can deliver low latency. So a couple of words about the presentation. So we will firstly speak about some approaches that are just match query with the document. And some of them, we will start from classic ones, and they are not machine learning at all. And we will move from heuristics based towards probabilistic, and from probabilistic towards machine learning. And then we will, I hope that we will have time to talk about maybe the most interesting part about ranking and the approaches and the philosophy that is used in ranking as well. Okay, so we start from the classic term frequency. So intuitively, whenever query comes to our search engine, what are the most relevant documents? The most relevant documents are the ones that have terms from the query and as many that occur frequently, right? We want to make sure, for example, if we're talking about textual documents, let's forget about PicsArt background for a second and think about documents like web pages. The most relevant documents should be the ones that have term from the query occur often. That is why we have this term here, TF, term frequency, for term T from the query for the document D. We put it in the logarithm because, yes, frequency is important, but the document that has 1 time occurrence of term T and the document has 10 times of occurrence of term T, the second one is not 10 times better, right? It's better, but not 10 times. That is why we need to smooth it somehow. We put it in the logarithm. And obviously, the overall weight or like score for the document here will be some query that happened to be in the document. That's it. Very easy. Another important part that kind of makes it more powerful is IDF, inverse document frequency. So the idea here is that not all terms are born equal. So rare terms are more informative usually than the frequent terms. So for example, if somebody searches for azure sky, the person doesn't search for blue sky. The person searches specifically for azure sky. That's why the document that has azure probably is more relevant than just the document that has sky. And we understand that sky occurs very often in the overall in our database, and azure probably is not that frequent word. So to account for that, we can use very simple calculation here as well, which basically says that we get the value of the size of all our database, the number of documents we have, and divide it by the number of documents that have term T, for example, sky or azure. And obviously, this value is going to be higher for the terms that are non-frequent, for the terms that occur in small number of documents. This is called IDF. And important observation that IDF is term specific, but not document specific. So if you have a query that is one word, IDF will be just multiplication by a constant. It's not going to change the order of your results. It's going to affect the relevant document list only in cases when you multiply, when the query is 2 words or more. Just an example. So we have different words. This column says the document frequency of words. We start from the rarest word, Kocharyan. I don't even know what does it mean. It occurred one time. And then that is occurs 1 million times. And imagine that the size of the dictionary is of database is 1 million. And then we calculate this value, right? So for Z, it's going to be 1 million divided by 1 million, which is 1, and log is going to give us 0. And for Kocharyan, we divide 1 million by 1, we get 1 million. And if the base of log is 10, then we get 6. So basically, we get positive reinforcement for rare terms. So obviously, in that case, the weight or score for term T in the document D is going to be just multiplication of term frequency of this particular term in the document D by the inverse document frequency of this term. And then obviously we need to do summation over all terms that intersect between document and query. And as I said, this is very basic logic, basic policy, but it works, and it increases with the frequency of query term in the doc, and also increases with the rarity of query term in the database. Why? It's frequently in the literature called vector space model, or similar models called vector space. Why? Because we can represent our query as a vector of size D or T, size of our vocabulary, how many terms we have. And term, it doesn't have to be word. It could be n-grams or some kind of way you want to encode your words. Again, it could be some stems and stuff like that. So it's size, the size of vocabulary vector that has in IDFs here. And if we represent our document as the same size vector of the same size with TFs, term frequencies, and then we'll just calculate cosine over between query and document, we will get the same thing, right? Because this is just multiplication for every single term for TF and IDF, and this is the dot product over all intersections, right? So we multiply, if we have IDFs here and TFs here, and then we do dot product, this means that we will multiply over intersection by TFs and IDFs, and then just normalize. So it's going to be the same as the same thing we did here. Advantages of those kind of models. Those models are simple. They can leverage any type of similarity that we want, and then any type of vector weighting. So not only TF, IDFs, anything you want. Disadvantages, they do not account for order of words. Can give the same value score for different documents often, and also only works with exact term matches. So like the term from the query has to be present in the document, otherwise it's not going to work. So azure sky and blue sky are similar phrases, but this algorithm does not know about that. So another approach to that that is more probabilistic, called binary independence model. It's also classic, and a lot of things is built up upon it. and build on top of that. The idea here is that we want to estimate probability of relevance of the given the query and the document. But in order to make this calculation tractable, there are some simplifying assumptions. Assumption number one, about binary. All our documents represented as a binary vectors, where 0 stands for term not present in the document and 1 for present. Independence. Terms are independent from each other. The occurrence or absence of the term does not affect the occurrence or absence of another term in the document. And another independence assumption, this probability is independent from other documents in the result. So probability of relevance in this model depend only on query and the document itself, but does not depend on the documents that appear on top or below this particular document, which is also wrong, obviously, because the document could be duplicates, and then very relevant document that is duplicated becomes non-relevant now. But we do these assumptions and we move forward. This is just Bayesian formula. This is Bayesian formula for the same, but for relevance equals 0. If we, again, there's one, for computational reasons, we can consider not calculating this probability, but calculating the odds, the division of those two probabilities. It will make computations easier, but the order will be the same, since the ranked order of the documents based on odds and probability is going to be the same. So if we divide here, there are some terms that cancel out. We come to this form. And here, since I said that we make an assumption that this is a document, right? And the document is just vector of words, or like set of words that even either occur or do not occur. And since they are independent from each other, we can represent the document as just multiplication of probability of occurrence of every single word in the document, because they are independent. So this is part here. This part on the left became odd, right? Why? Because this is this. This is the probability of relevance given query, which means that basically, given this query, what is the probability of the what is the probability of finding relevant document? And this could be estimated based on some historical data if you have relevance information, but we don't even care about that, because this value is constant for query, which means it does not change with the documents, so which means does not affect the order of the documents. So we just don't care. So we just forget about this constant value and move on. So we can express this since xt is the term that either occur or does not occur, since it's a binary model, we can rewrite this expression as these two expressions. The only thing here that in this case term does not occur, in this case term occurs, and then move on. So we simplify this just form by replacing this with pt. We just called pt just to make it easier to write all this stuff, and then this with ut, and obviously this will become 1 minus pt, and then this 1 minus ut. So we'll move through this quick. So if you are interested in all of these derivations and you want to go like more deeper, let me know. It's just I will give you a link, and then there's a book that goes through all of this in more details, and you will be able to go it in a normal pace. So we get the same expression rewritten here, and we do some trick here. So as you see, what does it say? It says we multiply over all terms in the query that are ones that occur in the query, and over all terms that do not occur in the document. And the same here, but we multiply over all terms that occur in the document. So if we make a trick and just include here all terms that also occur in this product, we can do that. But we just multiply by that. But in order to cancel this thing, we need also to divide it on the left side. So we will divide by this on the left side, and it's fine because this product is working for exactly terms that occur. So we kind of include terms that occur here and then divide by them here. And in that case, this right part becomes for terms that occur in query and all terms in the document that occur and do not occur. So we forget about this. Why? Because it becomes also document independent. So it's only kind of constant value for query. And then we divided by this, so we flipped it over. So U went up and PT went down. Why did we do that? You'll see in a second. So it will, so because we now don't care about this part and now don't care about this part as well, as you remember, we need to only estimate this value. And as usual, since we have multiplication, we can use log and then sum of log. Log of product is going to be sum of logs. And here, the question now is only to estimate PT and UT, right? And in practice, historically, let's say in pre-machine learning era, they did some kind of approximations here and used some heuristics. So what they did, for UT, they were saying, okay, UT is just probability of a term appearing in a non-relevant document, right? So we have a term appearing in the non-relevant document given query. So since non-relevant documents are majority and relevant documents are so small, we can say just reformulate this as a probability of just term occurring in any document, relevant or non-relevant, because relevant documents are a very small number. And see, if we do that assumption, we can replace UT as just DFT, which is the number of documents that have term T, divided by N, which is the size of the whole database. So if we do that, we will get to this form, and this form, since again DFT is negligibly small in comparison with N, so number of documents that term T occurs is much smaller than the whole database of all the available documents, we can just come to this. And if you remember this, log N divided by DFT is this, IDF. So IDF, something that was actually not derived by any theoretical approach, some kind of heuristics, actually with some simplifying assumptions get some theoretical justification, which is an interesting fact in itself. And for PT, since the probability of term occurring in the relevant document for the query, usually they use some big value, because if the document is relevant to the query, it should have, right? It should have the term. And often they use just 0.5, and 0.5 just cancels this part, right? Because 0.5 divided by 0.5, so this becomes 0. And then we left out only with this part, and we just understood that this part is just IDF. So this binary independence model with some simplifying assumptions just gives us the same idea. But we understand that IDF is, again, quite primitive approach. So what became a standard in the world of search engines in the pre-machine learning era was an algorithm called BM25 that is based on the same IDF, but just accounts also for term frequency in the document, term frequency in the query, and for a length of the document. The idea here that the more term occurs in the document and the more term occurs in the query, and the shorter the document, the more relevant, probably the more relevant document is. We can, and these K, B, and K3 parameters, they are just tuning parameters that if you put it higher, it will just give higher weights here. If you put it smaller, it will just give smaller weight. So let's move on. The main disadvantage of this approach, it actually simple, but works quite well. And it did perform well in different benchmarks and in different competitions. But it's quite primitive and accounts only for direct matches of the words. If we want to not just go through direct matches of the word, as I said, azure and blue are semantically similar words, but this model does not know about that. We can use just a singular value decomposition to turn document matrix. Turn document matrix in our database, we decompose, we get 3 matrices of eigenvectors and eigenvalues and eigenvectors again, which means that for we get latent space representation for our terms and documents, and then we can calculate similarity between documents and terms. If the query comes, we can get all terms from the query, average the value, get the representation for the query, get the vector for the document, and then just calculate similarity. And the main advantage here is that in that case, we don't need to have direct exact matches between the words. So query and document can have even all words different from each other, but still be similar. It's obviously computationally heavy. Imagine that you have a very big database of documents. It's not that easy to calculate that kind of stuff, especially since it was quite an old algorithm, and at that time, computational capacity was not that big. Another approach is also...
I'm sorry, Davidjan, we have maybe 2 more minutes.
Okay.
Yeah,
2 minutes for questions, or...
No, 2 minutes, then maybe 1 minute for question.
Okay. Okay, so since all of you know about word2vec and stuff, I will just go through this, and then we'll say that at the last stages, we want to rank documents. And just let's go through one algorithm, and that's it. So for ranking, there are different metrics. We will go through these metrics. I will just say about one matrix that the way you want to measure the performance of information retrieval is that to make sure that relevant documents are on top. So NDCG is one of the metrics that increases when a relevant document, this is the way it's calculated, and this shows the relevance of the document, this shows the position. So the more relevant document are on top, so the higher this value and the smaller this value, the higher NDCG. But okay, so features, learning to rank. So maybe just I don't think that I will be able to explain this in 2 minutes, so sorry. It's just a little bit too much. Or if you don't have questions and we have 4 or 5 minutes, I will be able to tell about it. So it's up to you guys.
Actually, there is one question. I think I'll ask you that question. And if there are additional questions, I think the people can write in Slack and you can answer them. So one question we get in the chat is, how do you spell check? And do you autocorrect words with typo on the top of it? Which techniques you use?
Okay, so
yeah, you have 2 minutes.
Yeah, for spell checks and for autocorrect. So basically in PicsArt, spell check and autocorrect is basically the same part of the same algorithm. So currently it forces for some queries, when it sees that it's written in some weird way, it checks for candidate queries that are close and forcibly replace it with the one that is close. Because if you don't do it forcibly, you will get a lot of zero unknown results for many queries, which is not a good performance from the user standpoint. But sometimes it's a false positive, so sometimes you get no result. You get it corrected wrongly. So it's not a machine learning techniques and stuff like that. It's a standard approach that employs stemming, lemmatization, and the Levenstein type of distances. So it's like out of the box approach. It's not like an algorithm. It's not a transformer network that looks for in some very big space for similar words or like phrases and stuff like that. Okay, so it's 1 minute, so I will not be able to explain that in 1 minute. So if there's any other question.
Yeah, I think the other questions can be asked in a Slack. So thank you very much for the interesting presentation.
Yeah. Sorry that it was going fast and could not finish in time. So I really apologize for that.
You can also put your presentation in a Slack so the people will can see the rest of your presentation.
Okay, sure.
Oh, Okay, thank you.
Yeah, thank you.